Okay, let's go. Yes. Ooh. I don't know, I'm not playing with that kind of latency. Maybe. Anyway, it's Crescent Bill versus. Shoot Crescent Bill. It's gonna be the close to yeah, bunch of damage. Anyway, I found out that's gonna be pretty boring. I can't breathe. You haven't I done so what's this? So we're going to. Well, what would deal with the berserkers? Probably a line of bomb throwers. Pirate Queen. Probably some harpooners to shoot down. The Valkyrie. Yeah, woman! I'm pretty sure So she has the bomb spin ability. So she'll be bomb spin. Yep! Bomb spin. Nice stuff. The campaign is a joke. Hey, what did you say? What did you say again? Oh, I'm just gonna... Terrorism, and more terrorism. Let's see how that works. Whoa. I think the strat is just blunderbusses. Lots and lots of blunderbusses. Oop, not the blunderbuss, and a flintlock for good luck. Their job is to sacrifice themselves. Did some work, so maybe just a captain on each of the flanks. A bomber. Oh yeah, and a bomber. I'm sorry, strategy is just not my strong suit, you know. Campaign is only a joke when you have rooms that can achieve the thing. Because I'm not laughing. Rolling again, better all in not rolling twice. Oh, good, not 20. You left the house from up, and I'm dead. Try dodging Okay, we cut down on the explosive by Pirate Queen. Yes! A perfectly timed. You're going to need I'm the archer. With sword. Yeah!
Be outside.
Mining with dynamite. The Stormcaster can take out a lot of the cast by just dodging. The ambush. Shit! Stop grasping for straw!
Change the bird!
Way!
Do you have a balloon on? Join a fencer. Hobbit decoys work extravagant. Just did not. So fast. Oh, you just disappeared into the Netherlands. A flock of vampires coming. There's a vampire tidal wave. They will suck off all the dead eyes. Yep. That strategy was so successful, I think that it may even work twice. Just gonna have a decoy here, followed up by a bunch of candle heads. Here's an idea. Blood buses and a flintlock. Hold on. There. Let the battle begin! Shoot through a barrel of armor! Yeah, that's what I... intimidating, but intimidating, but alas harmless. You know. Nom 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 nom! Nom nom nom! Nom nom! Nom nom nom! Nom nom! Block of vampires! Amogus. Blunderbuss spam, that's what I think. And then the vampires! Suck them! Suck them! Suck them up! Yeah! You suck them good. I probably mute something.
Come my way, and I'm more than happy to help out. We can always get you in touch with the correct wholesaler if you're unsure of who you should work with. So feel free, go ahead, take a screenshot of this picture. I will make sure that we send out a
Oh,
follow-up email
Morgos.
that's going to include the presentation we're going through, and any additional marketing materials that you guys need. So we'll have all of their information in my signature as well, but just keep in mind, there's my number there, 614-435-3010, and then ASHMOL, number 1, at nationwide.com. Feel free to reach out to me if you have any questions, any potential clients out there that you would like to talk through a case on, and we'll make sure that we get everything handled for you in that regard. So with that said, what we're going to do is we're going to start our presentation here. Now, as always, if you guys have any questions throughout the presentation, feel free to go ahead and ask those in the Q&A chat below. We will most certainly take some time at the end to walk through any questions you guys have, and make sure that you guys are all squared away, and hopefully you're able to take a little bit out of this presentation today, where you're able to learn a little bit more about long-term care, specifically the cash indemnity planning when it comes to Nationwide's Care Matters program.
Whoa, he updated his avatar.
And go through just a few disclosures here before we start. And we will be sending this presentation out following the call today. Next week, we're actually going to talk through the application process. So feel free to tune in next week. Invite any of your additional team members that you may have that may not be familiar with the application process itself. We wanted to talk through more specifically the product today, and then walk through the application next week. So like I
It'll be for me to.
reimbursement style policy. With indemnity, we're going to pay out that full benefit, no questions asked. So in the event that, say, you're not $8,000 benefit, you're only spending $4,000 a month, that's an additional $4,000 which you can put towards future expenses. Long story short, it's not sitting inside of that contract, and you're not risking losing any of those dollars in the event that you pass away without receiving. So let's take a look at how the product is set up and how it lines up with. So for example purposes, what we're looking at here is a $100,000 single premium. Keep in mind that's not the product minimum, just using it for now. Just to be able to understand how the product ultimately works. The plan, first of all, we want to claim is accessible through this booklet. Usually set these up on 2 seconds, but I'm going to set this one up to 4 so it's a 6-year plan. During those first 2 years, they are going to accelerate and you're going to see from that first plan, which is the death benefit. So this is the death benefit plan. It's $180,000. Say they were to get to 1 year of life and they were to pass away. We're going to take that back from their plan. So there's a residual death benefit attached. Then there's also the death benefit of 17 years. If they were to get to 1 year of life and they're only paying out $1 that's going to be the death benefit paid out to beneficiaries. We also set the cost base. United States already calculates 20% residual. So this is 20% based on that full deductible of $8,000 to be paid for an additional 50%. So this slide here is going to show you some of the fundamental differences between both products. So I mentioned earlier that life care matters in California and New York. Memory care matters in California. For those of you in California or those looking at doing business in California, we have had our first product approved in California. We're expecting a launch date most likely late April. Might be a little bit sooner. We will be on that as soon as we learn more about transition guidelines, things like such. But keep in mind, I'll be halfway this video. Note the differences there. The issuing is less scientifically motivated. The issuing is more through life care companies who are 30 to 75. And 75 are Medicare carriers too. So Medicare carriers too, it's going to be great.
Hamburger, hamburger, hamburger,
We're going to do a 90-day contract with any new carrier.
hamburger,
We're going to go ahead and discuss the contract with them.
hamburger,
So keep in mind, 90 days.
hamburger,
Some products
hamburger,
have been carriers for
hamburger,
this days
hamburger,
that will follow
hamburger,
immediately.
hamburger,
If you
hamburger.
hit those 2 days of payment, between those 2 days, we're going to do a termination period. We require calendar days, so it's truly 90 days, 3 months. Both products are going to have return of premium features. For
Wow.
hamburger, hamburger,
This is one of my favorite concepts because I believe it can be very Now keep in mind,
hamburger, 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 hamburger,
so you're sitting down.
hamburger, 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 hamburger,
Worst case scenario. One of those. White one. What's that? Hamburger. Oh no, my just take this and go. Sweet child, you're a
In 1901, the English philosopher and mathematician Bertrand Russell discovered a problem, a paradox, at the heart of mathematics and all of science. The paradox specifically concerns a foundational branch of mathematics called set theory. So, in this lecture, I teach you all of set theory in like 8 minutes, and then I show how the paradox arises. Russell himself and many other mathematicians thought that they could solve this paradox, but I argue that they can't, and they don't. So let's get started. What is a number? Take, for example, the number 4. I'm not talking about 4 potatoes, or 4 tomatoes, or 4 hairs. I'm talking about the number 4 itself. We know lots of things about the number 4, like that it is evenly divisible by 2, and that it's the square root of 16, I think. I'm talking about the number itself. And I'm also not talking about this right here. This is not the number 4. This is the Arabic numeral written on a piece of glass, the Arabic numeral that represents the number 4. We have other numerals that represent numbers like this one. That's the Roman numeral 4. We use it for counting Super Bowls here in the United States. The number itself is something that no one has ever seen or touched, but we seem to know things about, and also it, and every other number, is essential to science, technology, and all of human life. Immanuel Kant was a Prussian philosopher living in the 1700s. This painting of him was actually done in color, but I've changed it to black and white to make it seem even older. He thought that mathematics was a construction of the human mind. And if that's right, then mathematical truths are, in some sense or other, subjective. But the German and English philosophers Gottlob Frege and Bertrand Russell didn't like this. They thought that mathematics had to be objective. To refute and counteract Kant's view, they developed a view called logicism. According to logicism, mathematics is a branch of logic. And the most basic type of math, which is arithmetic, could be reduced to just first-order basic logic and set theory. I'll explain what set theory is in a second. They thought that if they could succeed in reducing arithmetic to logic and set theory, then they would be able to answer this question, what is a number? And the answer would be that numbers are sets. Okay, well, what is a set? A set is a collection of objects. The branch of mathematics that studies sets or collections of objects was invented by the Russian-German mathematician Georg Cantor in the 1870s. Cantor proved that some infinities were larger than other infinities. Yes, that's right. The idea is that you could have an infinite number of something and then an infinite number of something else, but that you'd have more of one than the other. Yes, it's wild. In order to do this, he had to invent set theory. And so now, I'm going to teach you set theory very quickly, but then set theory is going to run into a terrible problem. It's going to seem terrible. They're going to try to solve it, but then I'm going to show that they didn't really solve it. The version of set theory that I'm going to explain to you in the next few minutes is naive set theory. It's called naive just because it's the ordinary set theory that we can formulate in ordinary languages like English, and it's contrasted with formal or axiomatic set theory, which is formulated in an artificial logical language. You don't have to worry about any of that. A set is a collection of objects, like the set of these markers. There are 3 markers here, and the set of these markers contains 3 items within it. But the objects in a set don't need to be collected together in space or time. in order to be a set for the purposes of set theory. So on the one hand, we could have the set of those 3 markers, but we could also have the set of all of the people watching this video who are spread out all over the world. Maybe they're spread out throughout time. Moreover, the objects in a set don't need to be related to each other in any significant or meaningful way. Another set could be the set of LeBron James, the 4-time NBA champion, and the top half of the Eiffel Tower. These things have nothing to do with each other, really, but we have a set with those 2 things in them, those 2 members, those 2 items. Anything that we can refer to, anything that we can imagine, that can be in a set. We could have a set that consists of LeBron James, the 4-time NBA champion, and Harry Potter, the young wizarding boy who does not exist. That set contains those 2 objects, one of which has won an NBA championship 4 times as of the recording of this video, and the other one is a non-existent boy with magic powers. Indeed, sets can even include objects that can't be imagined. We could have the set of all objects that cannot be imagined. That's a set too. And it contains many, many things, perhaps an infinite number of things that can't be imagined. You see these squiggly brackets? The squiggly brackets are used in set theory to pick out the set. And all the stuff inside those brackets are the stuff in the set. So this is the set of LeBron James and the number 4. There are 2 things in this set, a number and a basketball player. On this form of notation, in order to pick out a set in writing, we would have to write out all of the things that are in that set. But that's too clumsy if it's a big set, like the set of all cats. The set of all cats includes many, many things, too many cats to list out. And also, we don't even know all the names of all the cats in the world, all the cats in the universe. So instead we use this notation, which is read as follows: the set of all x's such that x is a cat. That's called the set builder or intentional notation. You don't have to remember that. The other crucial thing is the word contains. We say that a set contains all of the objects that are members of that set. So this set from before contains LeBron James and the number 4. The set of all cats contains Garfield and all the other cats as well. A set is a many that allows itself to be thought of as a one. Georg Cantor never said that. Someone just said that he said that, but he didn't really say it. A set is a gathering together into a whole of definite, distinct objects of set to be thought of as a one. Other cats as well. A set is a many that allows itself to be thought of as a one. Georg Cantor never said that. Someone just said that he said that, but he didn't really say it. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. He did really say that, but he said it in German. When Cantor invented set theory in the 1870s, he wasn't just making up a mathematical game for the sake of it. No. We deal with sets every day. Suppose that someone says that pile of potatoes is enormous. They're not talking about the individual potatoes. They're not saying the individual potatoes are enormous. Some of them may be quite large, but some of them are small, like fingerling potatoes. I'm gonna try to find a photo of a fingerling potato or some other kinds of potatoes. Anyway, when we say that that pile of potatoes is enormous, we're talking about the pile, not the individual potatoes. And we do the same thing with objects that are not collected together spatially. The world population of cats is enormous. The cats aren't collected together in space, but we're talking about all of the cats as a whole. And we're saying that that population is enormous. We're not saying that the individual cats are enormous, although some of them might be quite hefty. The paradox, the logical problem that Russell discovers in 1901 concerns one or more of the rules of set theory. So let's go through some rules real quick before we can get to the paradox. Rule number 1, unrestricted composition. That just means we can make any sets we want. Any set that you can think of, that's a set. In the formal axiomatized version of set theory, this is called the axiom of unrestricted comprehension. You don't have to remember that. Rule number 2, set identity is determined by membership. What does this mean? It means that what makes a certain set, the set that it is just what's inside of it. It doesn't matter how we label that stuff. It doesn't matter how we label the whole set as a whole. All that matters is what's in the set. In formal axiomatized set theory, this is called the axiom of extensionality. You do not have to remember that. Rule number 3, the order of elements in a set doesn't matter. Here, for example, are 2 sets. The set of the number 1 and the number 2, and the set of the number 2 and the number 1. These two sets are the same set because the order that you put the items in, the objects, it doesn't matter. Now you can see this rule, this really comes from number 2. Number 2 says that set identity is determined by membership. All that matters is who's a member or what items are a member of the set. It doesn't matter the order. Rule number 4, repeats don't change anything. This set right here, which contains the number 1, the number 2, and the number 2, is exactly the same set that we were talking about 5 seconds ago. It's the set of just the numbers 1 and 2. If you repeat a number or a member of a set, it doesn't change the set because set identity is determined by membership. That's rule number 4, which is really just derived from rule number 2. Rule number 5, the description of the items in a set doesn't matter. For example, the set that contains just LeBron James and the set that contains all X's, all things, such that that thing is the NBA all-time scoring leader, playoffs included. I'm including the playoffs. If you only talk about the regular season, then Kareem Abdul-Jabbar, as of this recording, is still the all-time points leader. But if you include regular season and playoffs, then it's already LeBron James. Those two sets are the same set. It doesn't matter if you describe him as LeBron James or King James or the NBA all-time scoring leader. Either way, it's the same set containing the same one item in it, and that's that guy who's a basketball player. Rule number 6, the union of any 2 or more sets is itself a set. This rule just means that if you take 2 sets, like the set of all cats and the set of all dogs, and you combine them, and then you've got the set of all cats and dogs, well, that's a set too. This rule, number 6, comes from rule number 1. Because rule number 1 says you can just make any sets you want. So if you got 2 sets, and then you put them together, that's another set. You can make that one too. Rule 7, any subset is a set. A subset is just a set containing some of the items that are contained in another set. And that comes from rule 1 too. If you can make any set, then any set you've got, well, any group of those items in there, that's a subset, that's a set too. Rule 8, a set can have just one member. This set contains one item or one element, and that is LeBron James, 4-time NBA champion. A set with just one member is called a singleton set. One important thing to notice is that this set, this singleton set, is not the same as LeBron James. LeBron James is a 4-time NBA champion. This set, the singleton set containing LeBron James, is a 0-time NBA champion. It has never won an NBA championship, and it has never played a game of basketball because it is a set. This rule, rule number 8, also derives from rule number 1. If we can make any set that we want, well, then we can make a set with just one item in it. Okay, we are approaching the point where one of these rules is going to generate the paradox. It's going to blow the whole thing up. Hold on, it's coming. Rule number 9, a set can have no members. This set is called the empty set. You can write it like this with just the squiggles and nothing in between, or you can signify it with this, which is like a 0 with a line through it, which means nothing. This is an empty set, the empty set, or it's called the null set. The fact that there can be such a set just derives from rule number 1, unrestricted composition. You can make any sets you want, including a set with nothing in it. But it is derived from number 2, that set identity is determined by membership, that there's only one empty set or only one null set. That one set with nothing in it, it's defined by the fact that it has nothing in it. So if you have 2 sets and they're both empty, they're the same set, the null set. Now things get juicy. Rule number 10, you can have sets of sets. This just follows from number 1 as well. If you can make a set out of anything that you can think of, well, you can think of sets too, can't you? Sets can have sets in them. For example, the set of all singleton sets, you'd write it like this, which reads, the set of all x's such that x is a singleton set. That is a set of all sets. It contains the set that just includes LeBron James. It contains the set that just includes the number 17. It does not contain LeBron James, because this is the set of all singleton sets, and LeBron James is not a singleton set. He's not a set at all. He's a 4-time NBA champion. Or you could have the set of all sets, the set of all x's such that x is a set. This, by the way, is how Frege and Russell answered that question from before, what are numbers? They thought, at least they thought until Russell's paradox just blew the whole thing up, they thought that the number 1 just is the set of all singleton sets, the set of all sets with one member. And the number 2 just is the set of all sets with 2 members. Now you might be thinking, I can't wrap my head around this. What does it really mean for the number 4 to just be a certain set? What does that really mean? Don't worry, no one really understands what that means. Not really. Anyway, it doesn't matter because the whole thing is going to be blown up right now with the next rule, which is rule number 11. Sets can contain themselves. This one's weird, and it's going to give us the paradox, but that just comes from rule number 1 also. If you can think of it, you can throw it in a set. And so you can think of sets, and so you can throw sets in themselves. Consider, for example, the set of all cats. Does that set contain itself? No, because that set is not itself a cat. It's a set, and everything in it is a cat. So it does not contain itself. What about the set of all sets? The set of all x's such that x is a set. Does that set contain itself? Yes, that set contains all the sets, and it is itself one of those sets. So it contains itself. Or the set of all the things that I'm thinking about. This set doesn't usually contain itself, but right now it does, because right now I'm thinking of that set. Let's follow the pattern of thought that Russell was following in 1901 and 1902 when he discovered this paradox. He was just thinking about and developing this idea, rule number 11, that sets can contain themselves. Think about all the sets that do not contain themselves. The singleton set with just LeBron James. Does it contain itself? No. Because it just has one thing in there, and that's LeBron, not any sets, let alone itself. The set of all cats doesn't contain itself, because it itself is a set, not a cat. The set of all singleton sets, does that set contain itself? No, because there are a lot of singleton sets. And so the set of all singleton sets has a lot of sets in it. And so it is itself not a singleton set, it's got many, many members, many, many items in it. And so it doesn't contain itself. And then here are some sets that do contain themselves. The set of all sets, that contains itself. The set of all non-singleton sets, yeah, that set contains itself because there are many non-singleton sets. And so that set, the set of all non-singleton sets, has many members, and so it's a non-singleton set. So because that set meets its own condition, it is inside of itself. Or the set of all sets that have been mentioned in this room which is an endless black abyss from which I am speaking to you right now. Up until right now, that set did not include itself, but I just mentioned it, so now it does. Here's the next thought that Russell had in England in 1901. Okay, let's take all those sets that do contain themselves, let's collect all of them together and make another set out of them, the set of sets that contain themselves. Now we've got a set of those. We'd write it like this: the set of all x's such that x is a set that contains itself. Now let's take all of the sets that do not contain themselves, collect them together, make a set out of those. Russell thinks to himself in 1901 as he's barreling toward a paradox that's going to blow up the whole project to form the foundation of mathematics and all of science. This set that includes all of those is the set of all sets that do not contain themselves. And we'd write that like this: the set of all x's such that x is a set that does not contain itself. And then something happened. He realized a problem, and he wrote this problem in a letter in 1902 on June 16th to Frege. And Frege received the letter. This is what the letter really looked like. Frege got the letter, and it broke him. Physically, he had a breakdown and had to be hospitalized upon reading this 2-page letter. And the letter asked this question: the set of all sets that do not contain themselves. This set, does it contain itself? Here it is again. The set of all x's, the set of all things, such that x is a set that does not contain itself. Does this set contain itself? Well, let's go through both possibilities. If it does, then this set is in here, it's in itself. And the only way to be in there is to meet this condition, the condition of not containing oneself. So if this set does contain itself, well, then it meets this condition, and this condition says that it doesn't contain itself. If it does contain itself, then it doesn't. And consider the alternative possibility. If it doesn't contain itself, then it meets the condition. It's a set that doesn't contain itself. So if it doesn't contain itself, it meets the condition and then it's in there, which means it contains itself. So if this set doesn't contain itself, then it does contain itself. If it doesn't, then it does. And if it does, then it doesn't. So this set both contains itself and doesn't contain itself. And that's just a contradiction. So set theory doesn't work. That's the paradox. Now you might be thinking, oh, okay, well, that's no problem. Set theory was just some made up rules, right? That's how math is. We just make things up. Axioms are stipulated, which is to say made up claims. So we just made up all these rules, including Rule 10 and Rule 11. And Rule 11 is really the source of the paradox. Once you let sets contain themselves, well then, you're going to be able to formulate this set, and this set is the one that leads to the paradox. So let's just change the rules, right? Yeah. That's exactly what Russell tried to do. He tried to just change the rules of set theory. He made up some new rules, and according to his rules, sets cannot contain themselves. And that's what other mathematicians doing set theory
Epic
have done.
plus.
Like the Zermelo-Fraenkel set theory. That's a version of set theory with some restrictions. They just get rid of Rule 11. And of course, if you get rid of Rule 11, you say that sets cannot contain themselves, well then you also have to get rid of Rule 1. Unrestricted composition, or the axiom of unrestricted comprehension, or whatever you want to call it. So that's what all the mathematicians do. But does that work? Like, can we just change the rules? Back before, when we were going through all those rules, Rule 1 and Rule 2 and all the way up to Rule 11, were we just making up the rules? No, we didn't just make up the rules. And so we can't just change them. That was me. I just said that. What I'm going to argue for the next, 2 minutes, is that the rules of set theory are not made-up rules. They're real, non-made up, objective rules that already exist, and they govern perhaps one of the most fundamental practices of human existence, and that is predication. Now I have to teach you some linguistics. This is going to take, 60 seconds, 90 seconds, something like that. Once I've done that, I'm going to regenerate Russell's paradox and show that it was never a paradox just for set theory. It's a paradox for all of language and thought itself. Let's go. Here is a sentence. Garfield is a cat. It contains 4 words. Grammatically speaking, though, it has 2 essential parts. It has this first part, which is called the subject of the sentence, and it has this second part, is a cat, which is called the predicate. The subject is what the sentence is about. It's about Garfield, the cat. And the predicate says something of Garfield. It says that Garfield has a certain characteristic, and that characteristic is being a cat. LeBron is the subject of this sentence. He's the thing that the sentence is about. And Dunks, here we go, is the predicate. We can say that predicates are true of certain subjects. So the predicate is a cat is true of Garfield, and the predicate Dunks is true of LeBron, and it's not true of me. What was the relationship between sets and objects? The relation was containment. Sets contain objects. The objects are in the sets. What is the relation or the relationship between predicates and subjects? Being true of. Predicates are true of, or a predicate is true of a subject. What I'm going to do now is I'm going to leverage this similarity to try to regenerate Russell's paradox, but now it's not with some made-up rules of set theory, but with some very much not made-up rules of predication. And predication, let me just remind you, is just the practice of saying things about things. So the practice of predication is ubiquitous. It is utterly widespread. We do this constantly. We do it linguistically all the time out loud, and almost every thought we have predicates something of something. Remember rule number 1, unrestricted composition? For set theory, that rule was the rule that there's a set for any imaginable collection of a thing or of things. Well, that rule seems like it just is true of predication also. There is a predicate for any imaginable characteristic of a thing. Anything that you can say about something, there's a predicate for that. Of course there is. And those rules of set theory that allowed Russell in 1901 to generate his paradox, those rules of set theory, the relevant ones, they're just true of predication too. Rule number 10 of predication. You can predicate things of predicates, just like you can have sets of sets. Well, that's true. You can predicate things of predicates. Here's a perfectly grammatical English sentence. Is a cat sounds funny. Yeah, sure, kind of. It does kind of sound funny when you think about it. Is a cat, is a cat, is a cat. Sure, it sounds funny. In this sentence, the predicate is a cat is functioning as the subject of the sentence. Sounds funny in this sentence is the predicate, and it's saying something about the subject, which is the predicate is a cat. Sure, we can do that. That's a perfectly meaningful thing to do in any natural language. We can predicate things of predicates. Yes, we can. Can you smell where this is going? Predicates can be true of themselves, just like sets can contain themselves. Is this right? I think it is. Consider, for example, the sentence, is a cat is a cat. Is that true? No, because is a cat is a predicate. So it doesn't have a tail, it doesn't have fur. Is a cat is not a cat. But what about this one? Is a predicate is a predicate. Yes, that's true. Is a predicate is a predicate. It is. And that's a case where the predicate is a predicate is true of itself. It says of itself that it's a predicate, and it's right. So, rule number 11, predicates can be true of themselves. Some predicates, of course, are not true of themselves, like is a cat. We already saw that. Is a cat is not a cat, so that predicate is not true of itself. Dunks. Dunks doesn't dunk. Dunks is a predicate, so it can't play basketball, it can't dunk. So it's not true to say that dunks dunks. No, false. Tastes like chicken. That's a predicate. Something can taste like chicken. Does taste like chicken taste like chicken? No, it doesn't. Taste like chicken is a predicate, so it doesn't taste like anything. But then you've got plenty of predicates that are true of themselves. Is a predicate, so is a predicate is true of itself. Is a string of words a string of words. Yes, it is. So that predicate is true of itself. Typically comes at the end of a sentence. Well, typically comes at the end of a sentence does typically come at the end of a sentence. So that predicate is true of itself. Now, let's try to make a predicate that is true of all of the predicates that are true of themselves. And that predicate just is true of itself. Is true of itself is true of all of the predicates that are true of themselves. Fine, nothing wrong with that predicate. But then, what if we tried to make a predicate that's true of all of the predicates that are not true of themselves? That predicate would be is not true of itself. And now we're going to generate the paradox. I can't write this in a letter to Gottlob Frege because Gottlob Frege is dead, but I'm writing it in a video to you. Here's the question. Is not true of itself. This predicate, is it true of itself? Let's go through both possibilities. If it is true of itself, well then, what does it say about itself? It says that it's not true of itself. So if this predicate is true of itself, then it's not true of itself. If it is, then it isn't. What about the alternative? If this predicate is not true of itself, then it's not true of itself. But then it meets the condition set out in itself. It has this characteristic specified by the predicate. It's not true of itself. So if it's not true of itself, well then it's true of itself. If it is true of itself, then it's not true of itself. And not true just means false. So if it is true of itself, then it's false of itself. And if it's false of itself, then it's true of itself. So it's both true and false, which is a contradiction. And this isn't a paradox that we can just escape by declaring that there is no rule 11. In the case of set theory, yeah, maybe we could just declare that sets cannot contain themselves. But in the case of predication, which is just talking, in the case of saying things about things, We can't just declare that predicates cannot be true of themselves, because they can. This Rule 11, this just is true. And once you give me Rule 11, I'm going to generate the paradox. This is a paradox that we can't escape.
Alright, back with the audio. Oh, hell no. Send me back! Send me back for round two! It's a feeding frenzy! going? Just kidding, I don't have anything against furries. Digitally bad. I think this is. I've had you since the beginning, but I think you need a whatever.
Stop whistling. It's irritating.
Alright.
Paradox is a funny word. It's used for a lot of things that don't have that much to do with each other. Paradoxes are things that contradict themselves, or at least seem to contradict themselves in some way. That's about as specific as you can get while still fitting all the different things that people tend to call paradoxes. Now, I've come up with my own original system for classifying them. Paradoxes, one which I think is more helpful than just having one single definition. I think the best way to talk about paradoxes is to divide them into 5 categories, and each of those can have an actual proper definition. This is pretty different from most of the ways you'll see paradoxes categorized, but I think this method makes at least a little bit of sense. So, I'm Jan Measley, and let's go over each of these categories and have some fun with different examples in each type. That's it, that's the whole video, just listing paradoxes. Should be fun though. The first and most important type of a paradox is a logical contradiction. These are situations where every possible explanation can be shown to be incorrect. This is the primary definition of paradox, and the other 4 categories of paradox are called paradoxes due to their resemblance to these logical contradictions. I should note, in formal logic, the word contradiction doesn't actually mean this. It refers to just any time something cannot be true, whereas what I'm talking about are things that can't be true but also can't be false. So for those of you who actually study this stuff, keep in mind that when I say contradiction, that's what I'm generally referring to. One absolute classic paradox in this category is the liar paradox, which is as follows. This sentence is false. That's it, that's the whole paradox, short and simple. If this sentence is false, then it's true, because I said it's false, and it is. But since it's true, that means it can't be false. So actually this sentence is false, which means it's true. No matter what, you cannot meaningfully give this statement a truth value, because any possible explanation is wrong. It's a logical contradiction. This basic paradox has been restated in countless ways under countless names, but they're all just different takes on this one concept. It's really the most straightforward logical paradox you can have. Okay, so here's a more advanced example. I happen to really enjoy when paradoxes start with a really weird hypothetical situation, and the crocodile paradox, or sometimes dilemma, is a classic example of that. Let's say a crocodile kidnaps a child. The crocodile then goes to the kid's parents and is like, hee hee hee, I'll give you your child back, if and only if you can correctly predict if I'm going to give you your child back or not. So assuming the parents do actually want their kid back, what should they predict? Now's your chance to figure it out yourself. Okay, time's up. If the parents say, we think you will give us our kid back, crocodile, then the crocodile can do whatever it wants with the kid now, right? Like, it could say, that's right, you have solved my crocodile's riddle fair and square, so here's your child as promised. But it could just as easily say, tough luck, I have no intentions of returning your child to you, so now you will never see them again. And both answers would be following the rules the crocodile said at the start. But here's the tricky part. If the parents instead say, we don't think you're giving our kid back at all, then it's the same self-contradiction thing as the liar paradox. Because if the crocodile gives them their kid back, then their prediction was wrong, so the crocodile wasn't supposed to give them their kid back. But if the crocodile doesn't give them their kid back, then their prediction was right, so the crocodile should give them their kid back, as promised. No matter what, the crocodile cannot do what it said it was going to do. A paradox. Here's another classic. The barber paradox. This one is pretty well known. Suppose there's a town where everyone is required by law to be shaved, and there's a barber who shaves everyone who doesn't shave themselves, and doesn't shave anyone else. But the barber lives in this town too, and therefore must be shaved. So then, who shaves the barber? You often see this one framed as a riddle, where you're expected to come up with some clever workaround. And there's a whole bunch of clever workarounds, because this problem is usually stated in natural language like what I just did, leaving some things unstated that you can exploit. Depending on the phrasing, you could come up with various loopholes that make it so the barber doesn't need to be shaved at all. These self-referential paradoxes show up all over the place, and they all boil down to that same idea. You have some setup that leads to a statement that's dependent on its own truth value, so that if it's true, it's false, and if it's false, it's true. In general, whenever a logical contradiction shows up, it means that some assumption you made must be wrong. Sometimes, though, that assumption turns out to be, the system of logic I'm using to form this statement is internally consistent and doesn't have contradictions. If you have some sort of formal logical system, and it's possible at all to make a statement like, this sentence is false, then that proves that not all statements in that system can be shown to be either true or false. Does that make sense? Like, if you're hypothetically inventing the rules for an early version of set theory, and it turns out that it's possible to ask the question, does the set of all sets that do not contain themselves contain itself within the bounds of that system? That on its own shows that your system is inconsistent and has contradictions. Another common type of logical contradiction is when instead of having one thing contradict itself, two things contradict each other. There is a really unfun variant of the liar paradox that fits this description, but the most well-known example of this subtype is the irresistible force paradox. What happens when an unstoppable force meets an immovable object? These two terms are kind of poorly defined, but I think most people intuitively get what this is supposed to mean. If the unstoppable force is capable of moving the object, then the object isn't immovable. But if the immovable object isn't moved by the force, then the force isn't unstoppable. So then, at least one of these two things can't exist, because if they both exist, it's a contradiction. A more concrete version of this idea is like, say there's a sword sharp enough to cut through any shield, and a shield strong enough to block any blade. But of course, those two things can't simultaneously exist, because their definitions contradict each other, so at least one of those descriptions must be incorrect. An even more fun example of two contradictory definitions is the buttered cat paradox. As we all know, cats always land on their feet, and buttered bread always lands butter side down. So if you attach a piece of bread, butter side up, to the back of the cat, then drop the cat, what would happen? Since this one is describing real phenomena, there actually is a non-paradoxical answer here. The reason buttered bread usually lands butter side down is that the side with butter on it is heavier, but if the side that doesn't have butter has a cat attached to it, then clearly the side with the cat is heavier now, so you'd expect the bread to land cat side down. And unless the cat's reflexes are thrown off by having a piece of bread taped to its back, you would also expect the cat to land on its feet. Unless, of course, the adhesive used to attach the bread to the cat is relatively weak, in which case the bread and cat could become detached in midair, allowing the cat to land on its feet, and the buttered bread to land butter side down. Okay, you've got it, right? Cool, let's do a couple more subtle logical contradictions before moving on to the next category. There are infinitely many natural numbers. Some of them are interesting, and others aren't. What exactly it means for a number to be interesting is subjective, and will vary from person to person. But we can generally state that a number is interesting if it has some unique property that sets it apart from other numbers. If we assume, then, that only some natural numbers are interesting, then clearly there is an infinite set of natural numbers that aren't interesting. And in this set, one number must be the smallest uninteresting number, which is a pretty interesting property, which makes it an interesting number. This paradox is normally presented as a joke, the punchline being that this contradiction implies that all numbers must be interesting. Of course, there are several other assumptions that were made which led to that conclusion. It would make just as much sense to conclude that no numbers are interesting, or more boringly, that this notion of an interesting number just doesn't make sense to begin with, and cannot be precisely defined. One more contradiction before moving on to the next type, and this is one of my favorites in this category. It's another one with a weird setup, so you know it's going to be a good one. So, a prisoner is told that they're going to be executed at noon on a day at some point in the next work week. They're not told what day next week it'll be, because the judge wants to make sure that it happens when the prisoner isn't expecting it, for some unknowable reason. The prisoner thinks about this. The hanging will happen at noon on some day from Monday to Friday, and it'll be unexpected when it happens. They quickly realize that they won't be hanged on Friday, because if they make it past noon on Thursday without being hanged, then they'll know exactly when they're being hanged, so it wouldn't be unexpected. But since that means it must happen on some day from Monday to Thursday, then they can rule out Thursday too, for the same reason. And following that exact same reasoning, they can one by one rule out all 5 possible dates, concluding that the only way for their hanging to be unexpected is if it doesn't happen next week at all. So when they're hanged on Wednesday, it's completely unexpected. This paradox is great. Like all of these story-based ones, there's a lot of ways you could try to resolve the contradiction here, but in its purest mathematical form, it's a real pickle. There are a lot of angles people have taken to try to explain this one, and I'll be exploring none of those because I'd rather just move on. The second type of paradox is what I'm going to call a normal impossible question. This is a pretty weird thing to call these, so allow me to explain. An impossible question is exactly what it sounds like. It's a question that's impossible to answer. However, not all impossible questions are paradoxes. Bilbo's riddle, "What have I got in my pocket?" is an impossible question, but it does have a correct answer, and the person who asked it knows what the correct answer is. It's just impossible for anyone else to know the answer. This isn't a paradox, and it's also not a riddle. The other type of question I'm excluding from this category is impossible questions that are impossible because they're logical contradictions, since those were already included in the first group. So what I mean by a normal impossible question is a question that's impossible to answer, but not because there is a correct answer that's just secret, and also not because all possible answers lead to contradictions. This will be easier to understand with examples, and I have a decent amount of them. I'm pretty sure this is the third time I've mentioned the ship of Theseus in a video. It's a very famous thought experiment, and it's a great example of what I mean by a normal impossible question. For those who are unfamiliar, imagine a ship. As the ship ages, its individual pieces break and are replaced with new parts. Likewise, members of the crew grow old and retire. retire, and new crewmates are brought on to replace them. Eventually, the entire ship consists of replacement parts, and none of the original ship remains. So then, is it the same ship, or at some point in that process did it turn into a new ship? There's clearly something paradoxical about this question, but it's definitely not the same kind of paradox as a standard logical contradiction. After all, both basic answers to the question are logically consistent. There's just no real way to prove which one is definitively correct. There's also a bonus harder version of this paradox, where instead of the individual parts being discarded when they stop functioning, they're put aside, and then later all of those pieces are reassembled into the exact form of the original ship. So then you can ask, which of these two ships is the original? The ship of Theseus is very similar to another, much less interesting paradox, the paradox of the heap. Imagine a heap of sand. If you were to very carefully remove one grain of sand from the heap, it would still be a heap, but if you keep doing that for long enough, you'd have just one grain of sand, which isn't a heap. And 2 grains of sand are also clearly not a heap. So at what point in that process does the heap stop being a heap? This one is less interesting than the ship of Theseus because, to me at least, it's way more obvious what's going on. The word heap doesn't have a very specific definition, so there's no way to unambiguously say exactly how many grains of sand there are in a heap. This is true for most words, and people sometimes get really angry about this, but it's fine. There are, of course, some normal impossible questions that aren't just language tricks. The Boltzmann brain is a pretty freaky one. It's commonly accepted that simple explanations for things are generally more likely to be true than more complicated explanations. You know, Occam's razor. However, if this idea is taken to its extreme, you could ask about what the simplest possible explanation is for the nature of reality itself. After all, what's simpler? That the universe exists and is full of complex dynamic systems and sentient beings who can observe it, or that the universe is mostly empty, except for one disconnected brain that's hallucinating that it exists in a more complex universe. Thinking about this one too hard is a bad idea. So let's not. Aside from logical contradictions, the second most common thing people mean when they say paradox is a time paradox. A paradox caused by traveling back in time. These count as normal unanswerable questions, because in real life, time travel is probably impossible. The most well-known time paradox is the grandfather paradox. Suppose you went back in time and killed a much younger version of your grandfather. This would mean that one of your parents would never be born, and so you would never be born either. So you wouldn't be able to go back in time to kill your grandfather. That's a logical contradiction. But time travel is only a theoretical thing, and that's only one way we could imagine it working. There are other popular models of time travel where this isn't a contradiction at all. Like, say, going back in time creates an alternate timeline. So killing your grandfather would alter the course of that future, but not the future you came from. Or maybe weird predestination stuff happens that prevents you from killing your grandfather in the first place. A version of time travel very popular in science fiction. There are many different explanations we could come up with to explain what would happen to resolve the grandfather paradox, but there's no practical way to figure out which one is quote-unquote correct here, thus making this a normal impossible question. Subatomic particles have this annoying tendency to behave differently depending on if they're being observed or not. There's this concept of a superposition, where a particle can be in multiple states simultaneously, but once the particle is observed, the superposition collapses, and the particle randomly picks exactly one state to be in according to some probabilistic function. A lot of people, including a few famous scientists you've definitely heard of, have pointed out that this doesn't sound right. Like, there's no way that can be literally how it works, but it certainly appears to be the case from various experiments that I won't get into because I wouldn't do a good job explaining them. One huge problem with this particular model is that it's unclear exactly what counts as an observation, and that's where Schrödinger's cat comes in. So, completely hypothetically, let's say an evil scientist sets up a contraption where it makes some quantum measurement, like, say, detecting when a radioactive substance decays, and then, depending on its reading, will either do nothing or release some poison, and it has a 50% chance of doing each one. Then, this device is locked in a box with a cat. What happens? At a quantum level, a particle either decays or it doesn't, but nobody's observed it, so it's in a superposition of both states at the same time. Then, when the machine measures it, it either detects that the particle decayed, or it doesn't. But nobody observes this either, so the machine is also in a quantum superposition. So the machine simultaneously releases the poison and doesn't release the poison. This would mean that until someone opens the box to see what happened, the cat is in a quantum superposition of being both alive and dead at the same time. Unless the cat counts as an observer, then the superposition collapsed when the cat either got poisoned or didn't, or maybe the machine itself is an observer, so it collapsed as soon as the measurement was made. Or maybe this model of quantum mechanics is fundamentally flawed, and this notion of a superposition collapsing when observed isn't actually true, and there's some other way to explain the annoying behavior of subatomic particles that hasn't been worked out yet. Like other normal impossible questions, this isn't a logical contradiction, because there are plenty of ways you could explain this. It's just that nobody's come up with a way you'd ever be able to determine which answer is actually right. Okay, last one for this category. Assuming it exists, the universe is very big, and people have been trying very hard for a very long time to find signs that there is any intelligent life beyond this one planet, and yet nobody's found anything. So where is everybody? There are tons of possible explanations for the Fermi paradox, thus making it not a logical contradiction. But unless someone does eventually find proof that there is life on other worlds, this question is impossible to answer. Maybe we just haven't been looking hard enough. Or maybe we've already seen signs of alien life, but it's just so different from what we expect that nobody knew what it was. Or maybe there's alien civilizations all over the place, but they're just hiding for some reason. Or maybe life is rare and special, and Earth is just too far away from our nearest neighbors to ever be able to know they're there. So definitely not a logical contradiction, but it is still paradoxical, in a sense, making it a normal, impossible question. The third type of paradox is what I'm going to call a counterintuitive fact, or what you might see referred to as a veridical paradox. These are things that look like they're logical contradictions, but really are just provably true facts. From what I can tell just from talking to people about paradoxes sometimes, a lot of people don't think things that can be definitively resolved should count as paradoxes. A paradox shouldn't have an answer, you know? But that's the benefit of dividing paradoxes into these distinct groups, right? That way we can acknowledge that this is a different kind of thing from logical contradictions and normal impossible questions, but at the same time acknowledge that it is something that is often called a paradox. Anyway, time for some examples. An archer fires an arrow at a target, but if you think about it, how exactly is the arrow able to reach the target? After all, to get to the target, it must first make it halfway there, but before that, it must make it 1/4 of the way there, and 1/8 before that. You can keep dividing like this forever, and see that there are an infinite number of these points that the arrow must pass before reaching its destination. How is motion possible at all? This is one of Zeno's paradoxes, and it's not a contradiction, and it's also not an impossible question. This is simply a counterintuitive fact. Yes, you can divide any finite distance into infinitely many segments, and it remains finite. In the real world, there is a theoretical limit to how short of a distance you can have before it stops being measurable, but this is abstract math stuff, so we don't have to worry about that. Abstractly speaking, yes, all finite lines are composed of infinite points, and this is completely fine. It's a little weird if you're not fully comfortable with thinking about infinity, but it's certainly not a contradiction. Okay, this one starts with a puzzle. In a room with two randomly selected people, there's around a 1 in 365 chance that they'll have the same birthday. It's not exactly 1 in 365 because of the small chance of someone's birthday being February 29th, and calculating the probability of that is more involved than you'd expect, but the point is that it's about 1 in 365. But then, if you have 367 people in the same room, the chances that at least two people in there share a birthday is now 100%, because there aren't enough birthdays for it to be possible for every person in that room to have a different birthday, assuming that everyone involved uses the same calendar system when you ask them what their birthday is. So, somewhere between 2 people and 367 people, the chances of 2 people in the room sharing a birthday switches over from being more likely to not happen to being more likely to happen. So when does that switch occur? If you do the math, the answer turns out to be much lower than you'd probably expect. It just takes 23 people for the probability to be greater than 50%. And that's weird, isn't it? Like, really? Just 23 people? Huh. Probability stuff tends to be counterintuitive in general. The most well-known example of this, I think, is the Monty Hall problem. This has been explained a billion times, so I'll try to keep this one simple. So you're on a game show. There's 3 doors, and behind one of them there's some sort of fabulous prize, like a car or something. And behind the other 2 there's goats, which for the sake of the problem we'll assume you don't want. You're given a chance to pick one of those 3 doors, but before opening it to reveal what you've won, the host first opens one of the other 2 doors, specifically one that has a goat behind it. You're then given an opportunity to change your answer. Do you stick with your first choice, or do you switch to the final unopened door? A common guess is that changing your answer shouldn't matter, because there's only 2 possibilities, so it's a 50-50 chance either way. But in fact, when the host revealed where one of those goats is, that significantly changed the underlying probability. Let's analyze the different cases to see how. 1/3 of the time, your initial guess was the door with a car behind it. The host opens one of the 2 goat doors, and the final unopened door also has a goat. In this case, swapping is the incorrect choice. In the other 2/3 of cases, your initial guess was a goat. The host opens the other goat door, so the final door has the car, so swapping is the correct choice. Since this case happens twice as often as the other case, in general, swapping is twice as likely to get you the car as not swapping would be. I've found that this makes more sense when you think about what happens when there's way more doors. Let's say there's 100 doors and still only 1 car, and 99 goats. You make your choice, then the host opens 98 doors, revealing 98 goats. 1% of the time, you pick the car as your first choice, and the 1 door remaining is a goat door. And in the other 99% of cases, your first choice was a goat, and the host opens every single other goat door, and the one final door has the grand prize. In other words, the probability of getting the car when you switch is equal to the probability of your first guess randomly happening to be incorrect. The opposite of weird probability questions, naturally, is weird relativity questions. The faster you move through space, the slower you move through time. This usually doesn't matter, but when something moves extremely fast relative to an outside observer, it makes a measurable difference. Suppose an identical twin becomes an astronaut and goes to space. They then spend several years living in space, traveling on a cool science fiction spacecraft that can travel at speeds very close to the speed of light. However, when they return to Earth, special relativity tells us that measurably more time will have passed on Earth than the astronaut experienced while traveling at near light speed. For every 3 years they spend traveling at 80% of the speed of light, 5 years pass on Earth, meaning that they could spend 6 years in space and return home to find that they are now 4 years younger than their identical twin. This might sound impossible, which is why it's called a paradox, but it's just a true thing about the universe. Now for one of my favorite counterintuitive fact-type paradoxes, and a somewhat controversial one. Suppose you're trying to investigate the hypothesis that all ravens are black. Every time you find an example of a black raven, that's a little bit of evidence for the claim, and you can be slightly more confident that the hypothesis is true. But if you see just one counterexample, a raven that isn't black, then that would immediately disprove the hypothesis. Here's the weird part. The statement, all ravens are black, is in fact logically equivalent to its contrapositive, the statement, everything that isn't black isn't a raven, right? Like, these two statements have to either both be true or both be false. There's no way for only one of them to be true. Just like how every time you see a black raven, that's a little bit of evidence that all ravens are black, every time you see something that isn't black and isn't a raven, that's evidence for the claim that everything that isn't black isn't a raven, which means it's also evidence that all ravens are black. You might think that this sounds obviously wrong. Like, are you telling me that if I find a green apple, then just because it isn't black and isn't a raven, it counts as evidence that all ravens are black, the same way finding a black raven would be? On the face of it, it's just absurd. However, let's re-examine the claim. All ravens are black is a really weird thing to try to prove, isn't it? Because the only way to completely prove it would be to find every single raven and then show that all of them are black. But you actually still wouldn't be done, because you'd then also need to prove that you actually have found all of the ravens. And how do you prove that? Well, you'd need to demonstrate somehow that of all the potential counterexamples, none of them are ravens. Because remember, if just one raven that isn't black exists, that immediately disproves your claim. So you need to be completely sure that there aren't any before you can say you've completely proven the hypothesis. But if you actually have found all the ravens, then potential counterexamples are just things that aren't black. Most things that aren't black can be ruled out as not being ravens really easily, like green apples. But some of them would be birds that kind of look like ravens but aren't ravens. And if you were to completely prove that none of these potential counterexamples are ravens, that is, show that everything that isn't black isn't a raven, then that would complete the proof that all ravens are black. It's weird, right? It's very counterintuitive, and some people don't accept it at all. But there's no contradiction here. It's all completely sound as long as you agree with this idea that finding just one example of something being a certain way is evidence that all of that thing are like that. It might be a really small and insignificant amount of evidence, but yes, finding a green apple, a white shoe, or even a red herring supports the claim that all ravens are black. Let's think about the lottery. A whole bunch of people buy tickets, and then one person is randomly selected to win the jackpot. To keep the numbers simple, let's imagine a lottery where there are 1,000 people, and they all have an equal probability of winning. Every individual person, then, has a 1 in 1,000 chance of winning this lottery, a 0.1% chance. This means that you can say with 99.9% confidence that for any given person, that person will not win. However, even though it's reasonable to say that every person individually won't win, someone definitely will win this lottery. One person's ticket is guaranteed to be chosen. This, I hope, should make sense. This is normal probability stuff, but it implies something that's kinda weird. Even if two statements separately can be assumed to be true with high confidence, that doesn't mean that the two statements together can be assumed to be true with high confidence. More abstractly, if it is rational to assume A, and it is rational to assume B, it might not be rational to assume A and B. This isn't really a contradiction, but it certainly sounds like one, so it gets called a paradox. Speaking of gambling, imagine a game of chance played with a fair coin. All you need to do is flip the coin over and over. At the start of the game, the prize is $2. If you flip tails, the game ends and you take home whatever the prize is at that point. If you flip heads, the prize money doubles and you get to flip again. Mathematically speaking, you flip a coin until you get tails, and the amount of money you win is 2 raised to the power of the total number of flips. So then, on average, how much money are you expected to win playing this game? What would be a fair price for a casino to charge someone for a chance to flip this coin over and over? It's simple. Half the time you get tails right away, so you win $2. That's half of $2, so $1. If the first flip is heads, which happens the other half of the time, you have also a 1 in 2 chance of flipping tails and winning $4. So you have a 1 in 4 chance of winning $4, so we can add another $1 to the expected value. Then after that, there's a 1 in 8 chance of getting $8 and a 1 in 16 chance of getting $16, and so on. You can keep doing this forever. The probabilities get exponentially smaller, but the expected winnings get exponentially greater, at a rate which exactly cancels out the probabilities. So, the average amount you are expected to win from this game is infinity dollars, meaning a casino could charge as much money as they want for a chance to play this game, and it would always be a good deal. This paradox shows a key difference between the ideas of average expected value and the value you should expect. There is, in theory, no upper bound to how much money you could win playing this game. Exponential growth is a very powerful thing after all. Getting heads just 19 times in a row would get you over $1 million. It's just that the odds of that happening are, well, 1 in a million. Even though this is a game where half the time you only win $2, you have a very small chance of winning arbitrarily large amounts of money, which, when factored in, mean that, yes, mathematically, the average amount of money you'd win would be infinite. But that doesn't mean that's what you should expect, necessarily. Also, in practice, real casinos don't have infinite money. If we put an upper bound on how much money you can win before the casino stops you in order to prevent themselves from going bankrupt, you can get much more reasonable sounding results. To calculate the average amount you'd win, just take the base 2 logarithm of the maximum amount the casino is willing to give you, then round down to a whole number. You can do this easily by converting that maximum price into binary and counting how many digits long the number is. So, if you're at a casino that refuses to give you more than $1 million playing this game, on average your prize would be just $19, which most mathematicians agree is less than infinity. Imagine a bar. It can be a real one if you want. Now, no matter what this bar looks like, there is always at least one person there where you can say, if this person is drinking, then everyone at the bar is drinking. This is provably true, but it's a little misleading if you aren't completely familiar with how formal logic works. The thing that makes this work is that, I didn't say this property would always hold true for that person, it's just that at any given time, there is at least one person where this is true. Let's go case by case. First, if everyone at the bar currently is drinking, then you can actually say this about literally anyone at the bar. Yes, this person is drinking, and yes, everyone is drinking, therefore, if this person is drinking, everyone is drinking is a true statement. In any other case, at least one person is not drinking. In this case, this statement is true about everyone who isn't drinking. This person is not drinking, and not everyone at the bar is drinking, therefore it's technically correct to say, if this person is drinking, everyone is drinking. This definitely feels like cheating, I think, because it's using these differences between natural language and formal logic. You could rephrase it as, at any bar, there's always at least one person who isn't drinking, unless everyone is drinking. This means almost the same thing, but to me at least it's way more obvious what's going on. Last one of these before moving on to the final two groups, and this is a pretty simple one. Most people's friends, on average, have more friends than they do. Or, in other words, most people don't have as many friends as their friends have. This is a little bit weird, but it is measurably true, and for reasons that are relatively straightforward. So, okay, most people have an average amount of friends, but some people have a lot of friends, and also some people only have a couple of friends. You might expect that if you examine how many friends your friends have, that the distribution would be roughly the same, right? Like, most of your friends have a similar number of friends as you, but then some of them have a lot more friends, and some of them have a lot less. But this isn't actually true, because people who have a lot of friends are friends with a lot of people. The number of friends your friends have will be skewed, because you're way more likely to be friends with someone who has 200 friends than you are to be friends with someone who only has 2 friends. After all, 200 people are friends with that person who has 200 friends, and only 2 people are friends with that person who only has 2 friends. This means that the distribution of how many friends your friends have will be biased in favor of people with more friends, implying that, yes, most people's friends have more friends than they do. The final 2 categories of paradox are the most fun ones, and also the ones that are least likely to be considered paradoxes. The 4th category is the counterpart of counterintuitive facts. Counterintuitive facts, remember, are things that sound like they can't be true and that there's some sort of contradiction, but actually are true. So then, these are things that sound like they can't be true and that there's some sort of contradiction, and that's because they really aren't true. You sometimes see these referred to as falsitical paradoxes, but I call them math pranks. If you have a right triangle where 2 sides are 1 unit long, what is the length of the 3rd side? The answer is the square root of 2, but what exactly is the square root of 2? Well, what if we approximate it? This square has a perimeter of 4 units. These 2 edges, the ones that aren't shared by the triangle we started with, have a total length of 2. What we can then do is take this top left corner of the square and fold it inwards, like this, creating a 2-step staircase. As we can see, this staircase also has a length of 2. The thing is, we can just keep doing this, and at every step, the length is always 2. If we repeat this process infinitely many times, we can see that the length of this diagonal line is exactly 2. Therefore, the square root of 2 is equal to 2. This sounds like it can't be true, and that's because it isn't. It's a math prank. Multiple math YouTubers have done full deep dives into how this actually works, but the short version is that even though it looks like this infinite process keeps getting closer to the line we're trying to measure, the end result isn't really a line at all. It's a weird, infinitely zigzaggy thing. This method of approximating length doesn't work. Okay, here's a classic math prank. When you look into different falsitical paradoxes, a lot of them are just very variations of this one single idea. I'm going to call it the infinite chocolate paradox. If you take a bar of chocolate and make these specific cuts, you can rearrange the pieces like this, and what you get is the same bar of chocolate but with one piece left over. If you repeat this procedure over and over, you can get infinite chocolate out of just one bar. This sounds like it can't possibly be true, and that's because it isn't true. If you look really closely, there's a little gap here when you put the pieces back together, and that gap is the same area of the one extra piece. Again, there's a bunch of different labels this paradox has been given, and a bunch of different ways you can take one shape and rearrange it into something that kinda looks like the same shape but isn't. Another really common type of math prank is the various proofs that 1 equals 2, or that 1 equals 0. There's a whole bunch of these and they all do the same thing. If you break one of the rules of math, you get the consequences of breaking the rules of math. The fun part, of course, is seeing how subtly you can break the rules. This one, for example,
Two.
hides its trick in all this symbol shuffling. If you want to figure out what it's doing, now's your chance too late, it's right here. This step is a sneaky division by 0. Math prank. We already talked about the Monty Hall problem, but here's a sneakier one. You're given 2 envelopes. Both envelopes have money in them, but one of them has twice as much as the other, and you're not told which one is which. You then choose one of the envelopes at random, and you're given the option of either keeping the one you chose or keeping the one you didn't choose. And in fact, you can change your mind as many times as you want before committing to your final answer. So then, what should you do? Unlike the Monty Hall problem, you don't gain any information after making your first choice, so the probabilities should be completely unchanged. There is no reason it should make a difference one way or the other, right? Well, let's think about what would happen if you switched. The envelope you chose has some unknown amount of money in it. Let's say it's A. Half the time, you would have chosen the envelope with less money, so the other envelope has a value of 2A. The other half of the time, the other envelope has a value of A over 2. So, on average, you can expect that the envelope you didn't choose has a value of 1 1/4 times A. This is greater than A, so you should always switch. You can then go through the same line of reasoning a second time, and decide that you actually want to switch again. You can then keep doing this infinitely many times, never making a decision and never getting to keep either of the envelopes. This is, obviously, flawed reasoning, but it's somewhat controversial exactly what the problem in the reasoning here actually is. Here's the explanation I think makes the most sense. While it is true that if you switch you'll get 2A half the time and half of A the other half of the time, averaging these two numbers together is not helpful, because the value of A is different in these two cases. Let's say the value of the smaller envelope is X, so the larger envelope has a value of 2X. You have an equal chance of choosing either of these, so on average your initial choice will have a value of 1.5x. Then what happens when you swap? Half the time you're going from the smaller envelope to the larger one, so you're gaining a value of X, and the other half of the time you're going from the larger one to the smaller one, so you're losing a value of X. These two cases cancel out, so on average the net difference from changing your selection is 0. 3 guests check into a hotel. They're charged $30, so they pay $10 each. However, after checking in, the hotel manager realizes they made a mistake, and that they actually only should have been charged $25. So, a bellhop is given $5 and is instructed to refund it to the 3 guests. However, the bellhop, realizing that you can't divide $5 evenly between 3 people, decides that the better thing to do would be to keep $2 for themselves, and then give each of the guests just $1 back in return, and simply lie about how much the refund was supposed to be. So then, the 3 guests originally paid $10 $10 each, but they all had $1 refunded, so they really only paid $9 each, for a total of $27. Add that to the $2 that the bellhop took, and that's a total of $29. But at the start they paid $30, so where'd the other $1 go? The trick here is that this question seems to be asking one thing, but really it's asking a different thing. It looks like we're keeping track of what happened to the $30 the guest paid when they checked in, but we're not doing that. If you do keep track of where the money ended up, the hotel has $25, the guests were refunded $3, and the bellhop has $2. These numbers add to 30, just as you'd expect. So what's happening in the original paradox? The guests paid $30, but were refunded $3, so in the end they really paid $27. Of those $27, the bellhop has $2, and the hotel has the rest. What this paradox does is it takes the amount of money the guests paid and adds it to the portion that the bellhop kept. We took the number 30, subtracted 3 from it, added 2, then asked why the answer isn't 30. My favorite math prank, and I think one of my favorite paradoxes period, is the proof that all horses are the same color. In any group of horses, we can say that all the horses in that group are the same color if it is impossible to select 2 horses from the group that are different colors. So, under this definition, any group of 0 horses are always the same color. Additionally, any group of 1 horses are always the same color. Now, this is important. If we have a horse group of size 0 and add 1 horse to it, regardless of what color the horse we added actually is, this preserves the property that all horses in this group are the same color. This idea can be generalized to n horses. Let's say you have a group of n horses, and that you already know that any group of n horses are always the same color. Now, add 1 more horse to this group. This horse might be a different color from some of the other horses in the group, so we might now have a group of horses that are not all the same color. However, if we then remove one of the other horses from this group, we are now left with a different group of size n. We already know that n horses are always the same color, so that means that the new horse must be the same color as all the other horses in this group. And the horse we removed is already known to be the same color as the rest of the horses in the group, since it came from a group of horses that are all the same color. So if we now reinsert that horse, we now have a group of n plus 1 horses, which we can guarantee are all the same color. Therefore, if for some number n you know that n horses are always the same color, that means that any group of n plus 1 horses are also always the same color. And since we already know that this is true when n equals 0 or 1, then it must also be true for a group of horses of any size. Therefore, all horses are the same color. I love this one. The place where this proof goes wrong is actually surprisingly subtle. For a proof by induction like this, you need to prove that 1, something is true for some base case, and 2, that if something is true for n, that it must also be true for n plus 1. This proof almost accomplishes that. The trouble is that the argument for why you can add a horse to a group while keeping the group all the same color only works if the group you're starting with has at least 2 horses. Or, in simpler terms, the reason not all horses are the same color is that it's possible to have 2 horses that are different colors. The fifth and final classification of paradox is a very important one. Veridical paradoxes, or counterintuitive facts, are things that look like contradictions but are really true. Falsidical paradoxes, or math pranks, are things that look like contradictions but are really false. But what about the often overlooked category of things that don't even look like contradictions at all, but are still called paradox anyway? These are what I've decided to call one guy getting very confused, writing it down, and getting it published. These are paradoxes, where it's genuinely harder to explain what the contradiction is supposed to be than it is to explain why there really isn't a contradiction at all. This is my favorite category. A good place to start with these is another paradox themed around the color of horses. Did you know that white horses aren't horses? You might think that sounds wrong, but think about it this way. When you say horse, you could be referring to a black horse or a brown horse. But if you say white horse, you're not referring to a black horse or brown horse. That means that white horse and horse don't refer to the same thing, which means white horses aren't horses. This is just a confusing way to say the terms white horse and horse are not synonyms. That's it, that's the whole paradox. White horse doesn't mean the same thing as horse. Not really a contradiction, not even that counterintuitive. It's just a time one guy got really confused, and it's called a paradox now. Let's say a vote is held in a fair democracy. There are 2 options for policies up for vote, and the 2 options are mutually exclusive. Now imagine a person who's a really big fan of democracy. They love voting, so they decide to vote for the policy they believe should be enacted. But as a fan of democracy, they also believe that the policy that should be enacted is the one that gets more votes. So what happens if the policy they voted for happens to lose? On one hand, they believe that the thing they voted for should happen. But on the other hand, they believe that the thing that got the most votes should happen. But wait a second. Those things can't both happen. Make up your mind, hypothetical democracy fan. This one is very fun. I'm not even completely sure what assumptions you need to be making for this to even sound like a real contradiction. Like, yes, a person can accept one of two mutually exclusive outcomes while also having a preference for one over the other. Where's the problem? Sometimes you'll see a book that opens with a preface where the author acknowledges that the book might have errors in it. But when you think about it, or at least when you think about it in a really specific way, that's a contradiction. Because if the author went through all the effort to get the book published, that means that they believe the book is accurate. So then what's the point of... Wait, no they don't, right? I'm sorry, it's just so obvious why this one is just a nothing of a paradox. The author doesn't necessarily believe that their book is completely accurate. That's literally what the preface means. I tried to find and correct errors, but I am not perfect, so I might have missed some. This paradox is so good. It's another one that's supposed to be showing how someone has two contradictory beliefs, but like, that's just not what's going on here. The author spells out exactly what their beliefs about the accuracy are in the preface, David. This article has multiple issues. If you have an office on the bottom floor of a tall building, and you watch a nearby elevator, you might notice that the elevator goes up way more often than it comes back down. But that doesn't make sense. Where is the elevator going if it isn't coming back? Does the elevator escape into the sky, and then a new elevator grows out of the ground to replace it? Almost every paragraph on this Wikipedia article ends with citation needed. I should be fair to these one guy getting confused paradoxes. They're not always cases where someone genuinely thinks a situation with an obvious explanation is really impossible to explain. Often, they're used to demonstrate why a given assumption is false, the same purpose as many other paradoxes. My final example is a top-tier one guy getting confused paradox, and it accomplishes just that. A common assumption made in formal logic is that if A is B and B is C, then A is C. However, in natural language, this isn't always true. For example, the temperature is rising. The temperature is 90. Therefore, 90 is rising. However, the number 90 is not rising. It is remaining constant at 90. This is a contradiction. I love the temperature paradox. It demonstrates the differences between natural language and formal logic very well. Like, nobody would ever interpret these statements in this way. This is the white horses are not horses style of assuming that is means these two things are equivalent, when usually it doesn't. And if you interpret these statements not like that, the contradiction completely disappears. The temperature is rising means the current temperature is higher than what the temperature was recently. The temperature is 90 means the current temperature is 90 degrees. Therefore, 90 degrees is higher than what the temperature was recently. Which is true. It's not even remotely a contradiction. A perfect one guy getting confused paradox. Even if, in this case, the guy who got confused is just a hypothetical guy who exists so we can argue against them. What even is a paradox? From its common usage, there isn't really any single definition that covers all the things it can mean. But this is also true about most words. To understand how a word is used, giving it a precise definition is almost always the wrong approach. That said, I think the things that are generally called paradoxes can be put into 5 main groups. These are things that are logically impossible to explain, things that are impossible to explain for normal reasons unrelated to logic, things that appear impossible but are actually true, things that appear impossible because they're false and you got pranked, and things that don't seem that hard to explain at all and are in fact very easy to explain, but are just called paradoxes anyway. My list here is definitely not comprehensive, but I do think that at least the majority of things that are called paradoxes fit into these groups. Also, exactly which group one of these paradoxes belongs to is, like most things, highly subjective. What things count as unintuitive or what things appear to be contradictory depends a lot on what things you happen to know about. I don't have a grand conclusion here, so that's the whole video.
Come here. Give me a
Halt! Let's go. Easy. Palois is the best host, no contest.
There is a video game that doesn't exist. It's a myth, an urban legend, a hoax. It's called Polybius, and you might have heard of it. Let me take you back to 1981, back when arcade games were at their peak. A multi-billion-dollar industry and a fever that had a grip on pop culture. Video arcades were a new social nexus and had sprung up everywhere. Dimly lit by neon light, adorned with garish carpet, they played host both to crowds of teenagers and cabinet after cabinet of the hottest games of the era. Space Invaders, Pac-Man, Donkey Kong, Galaga. However, in an unnamed arcade in some sleepy suburb of Portland, there lurked something more obscure. A limited release of a game that would evaporate as silently as it appeared. The stories are vague. The cabinet is described as plain, and the gameplay? Weird looking, abstract, fast action with puzzle elements. Sometimes it's described as being particularly addictive, despite the unassuming appearance. The only concrete details are the name, year of release, and the company behind it. Polybius, 1981, Zinnis Lotion. Really, it was just like any other arcade machine, except for the side effects. Reports of sickness, amnesia, night terrors, and behavioural changes followed those who played it. It was no accident either, if you believe the rumours. Instead, a secret project by government agency, developed from military tech for the CIA or some other men in black. The machines were observed, gameplay records were taken, and then, after a month or so, they disappeared without notice, along with any shred of evidence. To this day, no authentic cabinets, boards, or dumped ROMs have surfaced. But there are some who claim to hold them. Quite the yarn. But could there be any merit to this myth, or even a basis in truth? It's probably safe to assume that the story has been subject to quite some embellishment. The accounts are full of conjecture and weasel words, supposedly, according to, etc. One thing remains consistent across all the stories, and that's the name. Polybius. Why Polybius? It's not novel, it belongs to a Greek of some repute, a prominent historian born in Megalopolis, Arcadia. This could be a deliberate choice to muddy search queries about the game, or perhaps it was chosen on its own merits. Polybius covered the Romans' rise to power in detail, an important primary source and an early example of rigour in historiography. He also lends his name to a simple cipher, the Polybius square, in which letters are substituted by their coordinates on a grid. Altogether, this doesn't tell us much, although the meaning of the name is interesting. The poly prefix means many, and bios, life. Many lives from Arcadia. Convenient. It could be a coincidence, but we can assume whoever named the game has at least some knowledge of either history or cryptography. Real or not, the name was chosen. Another word consistent to the myth is the supposed developer or publisher, Zinnis Lotion. It's a German word, almost. A not quite grammatical combination of Sinne, meaning sense, and Lotion, meaning to erase. To erase senses, to become senseless. It seems to allude to the mythical side effects of Polybius, which implies a deliberate choice. It's almost certainly not a real company, as there are no other games attributed to them, nor any trace of company records. So Polybius could be of German origin, but the incorrect grammar might also indicate the use of machine translation, something chosen by a non-native speaker to sound suitably obscure or sinister. There isn't much visual evidence for the game, and most can be discounted as fake. But there is one screenshot that is consistently upheld as canon. It's rather basic. A black background with a Polybius logo, copyright information and credits. And nothing else. However, compared to contemporary games from 1981, one thing stands out. The logo is unusually large and detailed. games that is consistently upheld as canon. It's rather basic. A black background with a Polybius logo, copyright information and credits, and nothing else. However, compared to contemporary games from 1981, one thing stands out. The logo is unusually large and detailed. Back then, fancy graphics were confined to the printed marquees. Every kilobyte of the ROM was valuable, so most game titles were rendered in the standard font, or at a much smaller scale. This did change over the next few years, and by 1983, larger, more lavishly designed title screens were more common. The closest match in terms of style might be from Nintendo. Their games favour large, bold titles with similar lettering. Perhaps Polybius drew inspiration from Versus Pinball or Duck Hunt. Of course, both of these date to 1984, which makes Polybius' 1981 claimed year of release look spurious. Perhaps it was just ahead of its time. Another detail from this screenshot is the font used for the smaller text. Those with a keen eye might recognise a similarity to those used by Williams games, such as Defender or Robotron. And it's definitely a close match, but they're not identical. The smallest 5-pixel high text does match Robotron, but the larger 7-pixel text does not. There is one game that comes closer. Nearly a perfect match. And while still a Williams title, it's the much less well-known Bubbles. It's still not a pixel-perfect fit, but it is closer than any other. The minor differences could be attributed to font hinting, JPEG artifaction, or perhaps a deliberate alteration. In any case, the text is distinctly Williams. Either Polybius is some lost prototype, or the image was fabricated by someone who drew influence from their games. The screenshot has been around for almost as long as the myth, and is likely the original source for the turquoise bubble-lettered logo. It doesn't exactly give us much to go on, and it certainly doesn't reveal what the gameplay might have been like. There are some that claim to reveal more of Polybius, such as these vector-esque images distributed on the now-defunct PolybiusLives.com. First emerging around April in 2008, there's little supporting evidence for their veracity. All signs point to a fan-made creation. Besides, it doesn't make sense. If you had the ROMs and were able to take screenshots of a functioning game, why not show it in motion? To see the game running would be a revelation. There have been multiple people who claim to hold the Polybius ROMs, and yet there's no sign of them anywhere. However, there is no shortage of gameplay footage out there, but these are all fan-made interpretations, impressions of what Polybius may have been like. One of the first emerged around April 2004, distributed by a site called GoodDealGames.com, the original source unknown. With a spooky icon, it's clearly supposed to evoke the myth, and those who are brave enough to run it are given a warning. The Polybius video game has been linked to impaired memory and psychological changes. Gameplay may cause epileptic seizures in susceptible individuals. Do you still want to continue? Click OK, and you'll be met with the familiar title screen, reformatted for a 4:3 monitor, with the logo rapidly flashing while a sound effect plays, a sequence of rising tones. The flashing continues until you press a key. And then, nothing. The game exits with a fatal error, and a message box that reads, "April Fools, send this urban legend to a friend." Interestingly enough, if you take the executable into a hex editor, you'll find the 2 MB file is not quite what it seems. The first 10 kilobytes consist of some data, but the rest? Empty space, acres of zeros, terminated with a few bytes of text. April Fools. so we can write that one off as an obvious joke. But there is another game that has become the dominant example when searching for Polybius gameplay. It came from a site at Zinnislotion.com, the supposed developers of the original. But the site explains that it's just a fan-made attempt to recreate what might have been. Launch the executable and you're presented with the obligatory warning screens. Do not play this game, etc. And ominous mentions of cognitive interfaces and higher functions. A familiar logo appears, but this is no mere prank. There's an actual game amidst all the spooky theatrics. The gameplay is admittedly simple, giving you control of a ship that can move in, out, or rotate the playfield. Like the original legend insists, there's more to the game than simple shooting. Glowing shapes bearing numbers appear, and if these numbers match either digit appearing on the base, or are evenly divisible, then you'll reduce the base's number by that amount. Once the base reaches 0, you advance on to the next level, where the visuals get progressively trippier. Aside from the puzzle element, the gameplay resembles vector games like Tempest or Star Castle, although some aspects are inconsistent with vector graphics, such as the swirling backgrounds. Entering the code 35, 34, 31, 54, 12, 24, 45, 43, the code that corresponds to Polybius on